So here we are now, starting chapter 14 on aldehydes, ketones, and chiromolecules. Hopefully so far you've been keeping up with everything, and we've taken those relatively simple seeming now alkanes, worked through the alkenes and alkynes, into the alcohols and phenols and uh, thiols and one other, ethers, right? So now we're ready for a couple more carbonyl functional groups now, aldehydes and ketones, and then we'll have our discussion of chiromolecules. Before we begin to discuss chiromolecules, let's wrap our minds around aldehydes and ketones. They've already come up, as you recall, I'm sure, from the reactions of alcohols. When we oxidize an alcohol, depending on whether it's a primary alcohol, if we gently oxidize it, we can get an aldehyde, or if we take a secondary alcohol, we can oxidize it up to a ketone. So we've seen these terms before, but let's get a better idea of what aldehydes and ketones are, how they're alike, how they're different, and how we name these things. So aldehydes and ketones are related. They both involve a carbonyl group, the C double bond O. In an aldehyde, that carbonyl carbon is bonded to a hydrogen atom, so it terminates on one side. So aldehydes are always terminal. They can grow any number of carbons the other direction, but the side that gets the hydrogen, that's it. The carbonyl and the hydrogen terminate the molecule. For a ketone, that carbonyl happens within the center of a or at least something that involves the carbonyl carbon being bonded to two other carbon groups. So we can have something as simple as a 3-carbon ketone, but we can't have any less than that. With an aldehyde, we could have a 1-carbon aldehyde, as we'll see. So that's the big structural difference. They both involve the carbonyl group as their key functional group, but again, aldehydes terminate on one side because that carbonyl group is bonded to a hydrogen, whereas ketones grow on both sides because they have carbon groups attached to either side of that carbonyl carbon. I can't say it enough that the condensed structural formulas, as convenient as they may be for beginning students, the skeletal formulas are really the way to go. So if we take a look at the aldehyde, we have our condensed structural formula there at the far left. Then in the middle we see a condensed structural formula that doesn't show the C double bond O, it just abbreviates it as CHO. That's a little misleading. You might think that the C bonds to the H and then the H bonds to the O. That's just not possible. In our course, we don't discuss bridging hydrogens. If you get into advanced inorganic chemistry, you might talk about 3-centered 2-electron bonds with boron and hydrogen, and things get really interesting there, but I'm guessing most of you won't be there for a while. So for our purposes, again, the C double bond O single bond H is probably the safer way to represent an aldehyde. Certainly the last extreme right representation, that skeletal structure, is much more convenient. It's much more what you're going to see if you look at books that have organic structures. So it's really where I hope you are, or at least are striving to be here in our course. For a ketone, same sort of deal. We can have it with the C double bond O shown in a condensed structural formula. We can have it where it looks like it's a CO in between. I don't like that as much because, again, it's misleading. You might think it's a C single bond O. It looks sort of like an ether there. That's not the case. Finally, at the far right, we see our skeletal structure. That's very clear that we have 3 carbons, enough hydrogens to complete the carbon 4 bonding scheme, and then the double bond to the oxygen in the center of that acetone molecule. So there we have it, some different representations. If you're going to stick with the condensed structural formulas, I'd prefer the ones on the far left. The middle, as I said, are misleading, although nice, shorter, easier to draw. But finally, the skeletal structures are the quickest to draw when you get the hang of them, and they show you all that good information. Okay, so let's pause here. Again, with this learning check, you're going to identify the following compounds as either an aldehyde or a ketone. So you know it's got to be one or the other. So don't think that A, for instance, is an alcohol, because that's not an option. So it's that sort of misleading representation I warned you about, but hopefully you can figure that one out, and you can figure B out as well. C and D are pretty self-explanatory, so hopefully you see that when you're interpreting the skeletal structure, it's easier. So hopefully you get in the habit of representing things by skeletal structures, so you can really look like and act like an organic chemist. Pause the video here while you make your determination for A, B, C, D, whether they're aldehyde or ketones, and then start back up to check your work. Okay, and here we have it. A is an aldehyde because we have that C double bond O, although we don't show the double bond O, but then single bond to H, so that's characteristic of an aldehyde. B, we have the CO, which is really a C double bond O on that middle carbon. Well, not quite middle because it's a 6 carbon thing, but on carbon number 3 there, we have that carbonyl, and we have carbon groups on either side, so that's a ketone. For C, we have a cyclic compound that's definitely a ketone because there's no way to have a ring structure with a carbonyl that's not a ketone, right? We can't terminate a ring, so that's clearly a ketone. The carbonyl carbon is bonded to 2 other neighboring carbon groups. And then finally, D is an aldehyde. We don't normally show that H. Sometimes you might see that H coming off of that carbonyl carbon, but typically it looks like we have it on the screen where you're just to understand there's an H there, like we always understand there's enough H's to complete the carbon bonding scheme when we use skeletal structures. Hopefully that went well. It was probably easier for you to pick out C and D than A and B, so hopefully you'll get in the habit of representing these compounds with skeletal structures. All right, so now that we got the subtleties of that structural difference, aldehydes having that terminal hydrogen off the carbonyl carbon, ketones having carbon groups off both sides of the bonding scheme from the carbonyl carbon, let's talk about naming these things. So we can pick them out now, hopefully, and if you can't, please do try some additional practice problems. Get in touch with me if the learning check and the practice problems don't go well, but hopefully you'll be able to identify them soon if you aren't already at that stage. Now let's talk about naming. Aldehyde has an IUPAC name in which the E, that would have been the alkane ending, is changed to AL, just like the first 2 letters of aldehyde. There's also common names, right? Like for many of these things, the common name for the first 4 aldehydes that use the prefix form, just like we had, well, we've had meth up to now. So form is probably new. We'll see it again when we do carboxylic acids, but form means it's a 1 carbon. Acid means it's a 2 carbon, propion means it's a 3 carbon, and butyr is the common abbreviation for a 4 carbon chain, all followed by aldehyde. So here we see IUPAC names. That would be methanal would be our first aldehyde. We don't have to indicate 1 because carbon of the carbonyl carbon is always going to be number 1 here since the hydrogen terminates. Common name formaldehyde. So you've probably heard of that substance, and you probably know it as a fixative, something that's a biological fixer and used to preserve biological tissue. For our 2 carbon aldehyde, it's ethanal according to IUPAC, or acetaldehyde by the common name. Propanal would be our 3 carbon straight chain aldehyde, and then propionaldehyde is our common name. And finally, butanal is the IUPAC, and butyraldehyde is the common name for that 4 carbon straight chain aldehyde. So not too bad. Just remember, especially form and acid and propion. We haven't seen those so far. We'll see them again with carboxylic acid, so get them down here and you'll be ready for that. Same thing with butyr for the common name there. If you want to apply the guides that we've been using previously, the guide to naming aldehydes is a pretty short one. It's a 2-stepper, right? The first step is to name that longest carbon chain by replacing the E in the alkane name with Al. Secondly, we didn't see it in that previous slide, but we have to name and number any substituents by counting that carbonyl carbon as carbon number 1. So this is the IUPAC naming. Again, we had some common naming for those first 4 that hopefully you've already gotten down. All right, so let's see how you do with some substituents. So give the IUPAC name of the following aldehydes. So for A, yeah, obviously there's a chloro substituent there, and then for B, you got to figure out how you're going to name that one. Pause it here, take your best guess, especially with B. See how you do on your own, then check with me, and we'll see how our answers compare. And certainly you can find lots more naming practice at the end of the chapter if you decide you need that. So pause the video here. Complete your work and start back up when you're ready to check that work. Okay, so the first step hopefully was the easiest. So we have for letter A, we have a 5 carbon chain there, and therefore that's a pentanal. It would be pentane if it wasn't a carbonyl at the end for the aldehyde. So that's our root name. And then for B, hopefully you remembered it. I didn't want to remind you unnecessarily. I figured we'd give you a shot there. But that's a carbonyl carbon of an aldehyde coming directly off a benzene ring. So this would be a benzaldehyde. All right, here now for step 2, we've got to number and name those substituents. Of course, the numbering should be fairly easy because that numbering, at least for a straight chain, the carbonyl carbon is number 1. So therefore, it's carbon 4 that gets the chloro group, and we have a 4-chloropentanal. For B, we have now carbon number 1 being the ring carbon that attaches to the carbonyl carbon. So that's a little different, and so the substituted benzene or benzaldehydes are going to have that feature. We number within the ring so that we get the lowest possible sum of those substituents. So rather than going clockwise and ending up with 6 for the position of the ethyl group, we end up going counterclockwise and hitting that as number 2. So that is 2-ethyl benzaldehyde. So hopefully those two names were not too bad for you. If you struggled with the benzaldehyde because you forgot about the benzene ring and how we name it, that's not too bad, right? Just hopefully now you won't make that mistake again. But please do practice additional naming problems if you're struggling with aldehyde naming. So now that we can identify and name these aldehydes, let's talk about some applications. Aldehydes are common in flavorings, for instance. So several of the naturally occurring aldehydes are used as flavors for foods as well as for fragrances. So benzaldehyde is that sort of almond odor. And then we have cinnamaldehyde is the cinnamon odor, and vanillin, of course we talked about it with the ethers in the last chapter, but it also has that aldehyde functional group as well as a phenol group. It's loads of fun, right? Vanillin has lots and lots of functionality, but here we're focused on that top aldehyde group. So the aldehyde group, in the case of benzaldehyde and cinnamaldehyde, that's the only group that could explain that particular odor and flavor. So aldehydes are not always very strong in odor, or even very pleasant in odor if you've ever smelled the formaldehyde we talked about as a fixative, but they are certainly capable of having some nice odors and flavors. Moving on to ketones now. Ketones are named in the IUPAC system by replacing that E in the alkane name with ONE. So the AL for aldehyde, the ONE for ketone. So we have the beginning of aldehyde is the end of the name for an aldehyde. The end of the ketone, ONE, is the end of the name for a ketone. So that works out nicely. With a common name, we can also do so by indicating those alkyl groups attached to the carbonyl carbon in alphabetical order followed by the ketone. Notice there we don't have numbering present. So if we look down at these examples, we don't number it as 2-propanone because there's no other way to have it, right? If it's propanone, there's 3 carbons, and carbon 2 has to have the carbonyl because we can't have a ketone at the end of a molecule. However, when we go over to the butanone, we do have to say it's 2-butanone. That one's a little interesting too because you can't have a butanone be anything but 2, but you could have a butanedione, which would be 2,3-butanedione. So we do keep the 2 there as just because of that possibility. So our common names, of course, have no numbering: dimethylketone and ethylmethylketone for those substituents. It's just the alphabetical order there that determines which group comes first, not the size of the group, as you can tell, because the ethyl group comes before the methyl group in ethylmethylketone. Okay, so here's our guide to naming ketones. First, we name the longest carbon chain by replacing that E in the alkane name with an ONE. Secondly, we number the carbon chain from the end near the carbonyl group so that we hit that number of the carbonyl carbon as low as possible and then indicate its location. Finally, we name and number any substituents on the carbon chain, and of course this is the IUPAC naming, but that's the naming scheme that we prefer. So let's pause here so that you can see how you do with naming ketones with this learning check. In this particular learning check, you're asked to give the IUPAC name for the following ketone. So there it is. Hopefully coming up with that IUPAC name won't be terribly difficult, but do pause the video while you figure it out and start back up when you're ready to check your work. Good luck. Okay, so step one, we named the longest carbon chain by replacing the E in the alkane name with ONE. So this happens to be a cyclopentanone. So that's how we would name it. Of course, since it's coming right off the ring, we have no choice. We can't decide to break the ring apart just to grab those other two carbons. They're going to have to be substituents. So there we have it. Cyclopentanone is the base name for this ketone. Moving on to step two here, we number the carbon chain from the end near the carbonyl and indicate its location. So instead of going clockwise, again, we're going to go counterclockwise to hit that substituent at a smaller number. So we end up with a 3 instead of a 4 if we had gone clockwise. So now we have a 1 cyclopentanone, but we've got to worry about that substituent. Okay, and now step 3, we name and number any substituents on the carbon chain. So we have an ethyl group at carbon 3. So this is 3-ethyl 1-cyclopentanone. Again, since it is assumed that the cyclopentanones or any cycloalkanes that we oxidize to ketones are going to have that ketone in position 1, but still we could have multiple ketones present, so therefore we do still include that 1, although it seems a bit redundant here. Looking at some common uses for ketones, they tend not to have as pleasant odors as some of those aldehydes, fairly unpleasant odors. Most people would agree on the ketones. They're often solvents. Nail polish remover is typically acetone or propanone, which is just another name for acetone. Dimethyl ketone is another name as well. Again, common names prevail, right? We don't see any of these aside from propanone is the IUPAC, but we don't see acetone doesn't even fit our common naming scheme that dimethyl ketone does. So you have to be careful. Even the common names get misused. If you've ever seen methyl ethyl ketone, MEK is often sold as a paint remover if you're in the hardware store. So you may have seen MEK. Again, that violates our rule that they come in alphabetical order when we named that substance as ethyl methyl ketone early on, and now you see that at the hardware store they might call it methyl ethyl ketone instead. So be careful of those common names, but for acetone you're almost never going to see propanone, you're almost always going to see acetone. So just get used to it that some common names aren't going anywhere and they actually predominate compared to IUPAC. Let's pause for another learning check. This time we're going to classify each of these compounds as an aldehyde or a ketone. So go ahead, stop the video here while you make those determinations, and once you've assigned aldehyde or ketone to each of these 4 structures, start back up and we'll see how you did. Okay, so A, we have that carbonyl carbon bonded to 2 other carbon groups, and therefore we must have a ketone. For B, we have the carbonyl with a hydrogen on one side and a carbon group on the other, so that's an aldehyde. For C, we have, again, a carbonyl carbon bonded to a hydrogen on one side and then a carbon group on the other, so that's an aldehyde again. And finally, D, when we've got that carbonyl carbon on a cyclo anything, it's going to be a ketone because we can't have a cycle unless we have at least 3 members. We talked about cyclopropane having lots of ring strain but still being stable enough to exist. So we couldn't have an aldehyde in a ring. It's just not possible. So hopefully come exam time I'm kind and go for a cyclo substance for this determination, because there's no doubt it's a ketone. Hopefully they were all pretty easy though. Aldehydes stick out as well in my opinion, so if you're not finding that to be true yet, I think you just might lack a little practice, so please do try some additional classification problems to identify the difference between aldehydes and ketones. Hopefully you have the aldehyde and ketone differences well underhand. So let's complicate things just a bit by adding some more functional groups with oxygens present. So for these 4 substances, classify each as an aldehyde, a ketone, an alcohol, or an ether. So stop the video here, please make those assignments, and then check your work. Good luck. All right, compound A has the carbonyl, carbon groups on either side, therefore it's a ketone. B, we have an oxygen that bridges 2 carbon groups, that's characteristic of an ether. For C, we have a carbonyl group with a hydrogen bonded to the carbon on one side and then a carbon group to the other, so that's an aldehyde. And then D, we have an OH group bonded to a carbon, that is an alcohol. Again, if it were the OH group bonded directly to an aromatic ring, it would be a phenol, but this is not that case. This is a straight chain alkane that has an oxygen on the middle carbon and then a hydrogen to terminate that oxygen, and it's a regular old alcohol here. So hopefully you're seeing how chapters 13 and 14 can go together, right? We made the ketones from secondary alcohols, we made the aldehydes from primary alcohols, so they are related by chemical reaction, but they also are different, and hopefully you appreciate those differences. You're probably hoping I forgot about the naming stuff, right? It was probably relatively easier to pick out the class rather than to worry about the details of the naming. So never fear, I didn't forget, and you do have to know those naming schemes. So in this case, you're going to name each of these as either aldehydes or ketones according to IUPAC rules. Pause the video while you do that. Good luck. Okay, so the first one looks kind of big, but the name isn't too bad. It's just a straight chain pentane that has that first carbon as a carbonyl group, and therefore it's a pentanal. For B, we have, if you were careful, right, that was a chloro group at the beginning, not a carbon, right? Carbon should have had 4 bonds to something else anyway, and so we have a 3-chloropropanal. We don't have any choice but to number that carbonyl carbon as 1, and therefore the third carbon bears the chloro group. Finally, for C, we have 2-butanone, right? 4 carbons. We start numbering from right to left because that'll give us the lowest number for the carbonyl carbon. Okay, so hopefully those went well. If that's not the case, well, we'll do another naming learning check in a moment. Okay, here we are as promised. Now you'll name these compounds. So go ahead, pause the video while you make those naming determinations, and then once you've correctly named each of these, we'll start the video back up to make sure you really did correctly name them. Good luck. So for A, it's definitely a ketone, right? Because we have carbon groups on either side of the carbonyl carbon. So if we use IUPAC rules, we find this to be 2-pentanone, right? It's carbon 2 when we number from right to left versus carbon 4 if we number from left to right. So the correct name is the name with the lower value for the carbonyl carbon. If you wanted to do the common naming system, this would be methylpropyl ketone. For B, that's good old cyclohexanone. There really isn't any other way you would name it. I suppose you could say 1, but it's always going to be a 1 for the position of the ketone in a cycloketone. For a C, we have 3,3-dimethylbutanal, right? The longest carbon chain is 4 carbons. The first carbon necessarily has to be that carbonyl carbon. Therefore, when we count out, those methyl groups both appear on carbon 3, and that's why we have to say 3,3, and then of course the di to indicate that those substituents are both methyl groups. So 3,3-dimethylbutanal. Hopefully that went well for you, and you've gotten down the ability to name from a chemical structure. And before we leave our first lecture on aldehydes and ketones, let's see if you can go the other way. So here I give you 3 names. So the task is to draw the condensed structural formulas, or better yet, those skeletal structures for each of those substances. So please stop the video here while you do that, and then once you have your structures, start back up and we'll check your work. All right, so 4-methylpentanal, well, the easiest thing to do is just go ahead and draw the pentanal, so 5 carbons in a row. We know that the first carbon would be the carbonyl carbon, so you could have had that at the far left. In this case, I have it at the far right. It doesn't really matter as long as it's in the right, one or the other, right places. And then finally, however you did that, you'd have to make sure to add the methyl group onto carbon 4, wherever carbon 4 might be in your representation. For B, we want 2,3-dichloropropanyl. So propanal is the 3-carbon chain with obviously an aldehyde, so therefore at one of the terminal carbons. Then go ahead and draw a chloro bond on carbon 2 and another chloro bond on carbon 3. Complete everybody with hydrogens, and you've got your 2,3-dichloropropanyl. And finally, for C, I would suggest you draw the butanone first, and then go ahead and put a methyl group there on carbon 3. And like I said, for any of these, you might have the mirror image of them just flipped right for left. It's still correct as long as you did everything correctly. If you're not sure if you did it correctly, then send it over to me. I'll be happy to take a look and send back my comments. Hopefully things are going well though, and you don't even need to check with me because you know you got these right, even if they don't look exactly like what I have. But if that's not the case, if you are struggling, we've just started aldehydes and ketones, so don't let it continue to bother you. Let's get it figured out, try some additional practice problems, reach out to me for guidance, and we'll make sure that aldehydes and ketones are making more sense than they may be at this moment. Otherwise, if they're making great sense, I'll see you in the next lecture on the aldehyde and ketone topics.